So today we're going to look over Coulomb's law. What I gave you is the first calculus-based homework assignment. It will be due in 2 weeks. After today's lecture, you'll be able to do 2 or 3 of the problems. You won't be able to do all of them after today's lecture. So notice I gave you 2 documents. The first one is the homework problems. These are all on Moodle, of course. And the second one is the rubric, what I'm going to grade it on. So you know exactly what I'm looking for each step. Right? So there's not any confusion. Like, I didn't realize that was what you wanted. And notice it does say things like use accurate, careful drawings with a ruler. Where this assignment came from is a few years back, I had a physics major taking the electricity magnetism class at University of Nebraska. And the first day of class, the teacher gave them this assignment for them to do. And he said, you should have learned this in your college physics class, so it should be easy for you. And I figured if he considered this is a good gauge of you should have learned this in your college physics class, I'll give it to you as an assignment in the college physics class to make sure you learn the stuff that he considers you should have learned. So one thing to note right off the bat, those problems don't ask you for the force, the electric force. What do they ask you for? Like the first one, what does they ask you to find? Of the don't have one in front of me, but I'm pretty sure it says of the electric field. Okay, E. It says E. E is the electric field. And so I have to start, we'll learn about the electric field probably in class mañana, but I'll start with telling you what the electric field is just so that you have everything you need. Electric field is exactly analogous to gravitational field. So do you guys remember what the gravitational field was?
The formula, or how to describe it?
Either one.
The formula was G lowercase m capital M over
You're doing the electric force equation, or not electric force, the gravitational force. The electric field was defined as, this is the definition, the force of gravity, what you were describing, divided by mass. And it was from that relationship that we used the weight of an object is force is equal to mg, because g was by definition the gravitational force divided by mass. The purpose of the gravitational field, G, was to make our calculations easier. On the surface of the Earth, G was always pointing down. You find its direction is down. And so the direction of down changes as you go around the Earth. And the magnitude of G, we learned that it does vary a little with elevation. But on the surface of the Earth, it remained roughly constant. Well, with electric fields, we're going to have the magnitude of our electric field changes a lot, but the definition will look the same. So the field is the force, the field vector is the force vector divided by the charge. It was gravitational charge for the force of gravity. So gravitational charge was m, hence the gravitational field was the gravitational force divided by the gravitational charge, force of gravity over m. Given that definition, how do you think the electric field is going to be defined?
The force of electricity divided by the charge?
The force of electricity divided by the charge. That's exactly right. Because I said it's completely analogous. It has to look the same. And so Coulomb's law, as we learned it yesterday, and I'm going to do one problem in lab today with Coulomb's law just to make sure people are a little comfortable with that. I realized, well, you got homework where you have to do calculation with it, and I just showed you the equation and said, it's just a force. Probably would be good to remind you how we work with forces. That's why I'm going to do that in lab. So the electric field is just the force divided by charge. Now, we learned Coulomb's law in class yesterday. So here's the equation that Charles Augustin de Coulomb came up with. This experimental equation that said the force vector is the first part. I have a more fundamental set of constants. 1 over 4 pi epsilon sub 0. Epsilon sub 0 is on the next slide. It's the permittivity of free space. That epsilon sub 0 tells you how easy it is for charge to go through a vacuum. And so that's just a constant, the 1 over 4 pi epsilon 0. And so to make our lives easy, we write it as K sub E. So those are the same thing, just two different ways of writing it. The one on the left is more fundamental because it's going to a fundamental constant. That epsilon sub 0 is a fundamental constant, whereas the K sub E is a derived constant based on the fundamental constant. Charge 1, charge 2 over r squared. And then I have the r unit vector here I just had the unit vector. So that's the Coulomb's law force. So if I was going to use, there's some important things to note here. Electrostatic. What does static mean? Yeah, not moving, stationary. I know stationary is a little redundant because you define a word by its meaning, or by itself. But static means non-moving. So this equation is an equation that works for stationary charges, not for moving charges. So we're studying electrostatics now, not electrodynamics. A second thing is this is for relating point charges. The charge between, or the force between 2 point charges. What is a point charge? Well, let's start with, you've all taken a math class somewhere along the way. A lot of them, I'm sure. And did you study what a point is?
Yes.
And can you define it in some way other than, a point is a point? Okay, it has, she said, no length or width. We usually simplify it to no volume. Because we live in three-dimensional space, it'd be no volume. Length, width, or height would be, using the one-dimensional in each of the 3 dimensions. Length or width would be 2 dimensionals, which in a math class is usually what you're doing because, you can put that on paper. So the point is it has no volume, no size. So that's saying we have charge at exactly that point and charge at exactly that point. That doesn't really exist. Well, electrons. As far as we know, electrons are point charges. We can calculate a maximum radius for electron, but we treat them as point charges as far as we know. That's how they work. But for something like this, that's certainly not a point charge. When I charge that up, the charge is spread out over a surface. But if you get far enough away, you could say that was close enough to a point. So we still use this and it has a lot of usefulness, even though charge is not at a point. Now, given this equation, what do you suppose the equation for the electric field due to a single point charge would be?
That equation over the point charge.
Okay, and now we have our first point of a little confusion with the symbols. I put Q1 and Q2 and then I put over Q. What were Q1 and Q2? They were the 2 point charges that were interacting. If I'm finding the electric field, what I'm finding is the thing that I can multiply my second charge by to see what force the first charge is going to put on it. So what I'm dividing by has to be one of the two charges, and usually I don't care, and I just say, okay, let's call this 2 just for grins, so I can say, oh, look, the two Q2s are going to cancel, and I'm just going to write this as this. Notice I dropped the subscript on the Q because now I'm just looking at the electric field due to a point charge Q. And then if I bring another point charge out, then I'll say the force on this point charge due to the electric field from that point charge is, and I'll multiply E times Q. So that would be Coulomb's law in electric field instead of force. Fundamentally, they're the same thing, right? Any physicist will say, oh, well, that's the same equation. We just solved it for a different variable. Of course, this is all non-calculus stuff, right? This is all algebraic. So where does calculus come into this? What do you think?
When you don't have point charges.
When you don't have point charges. When you have charge spread out over a surface, what you have to do then is, if you're using it the way we learned yesterday with the force equation, you would have to add up the force vector between each piece of that charge spread out on this object. Or if you're doing an electric field, you just find the electric field at this point due to each piece of charge on the object. And so due to each piece of charge, that's where you have to do the integral. Here's the definitions for the constants. I'm just going to exclusively use this for now. Now we will learn next week about Gauss's law, and when we use Gauss's law, I will be using the epsilon 0 in Gauss's law because it's less writing the 4 pi is the difference. But see the epsilon 0, it does have C in here. And I told you it was a fundamental constant. Now we see that it's 4 pi times 10 to the 7 times another fundamental constant because the speed of light is 299792458 meters per second exactly. That's considered a fundamental constant. But so is this. They're both considered fundamental constants. Neither one is considered a derived constant. And it turns out that there's a relationship between 3 fundamental constants here. The speed of light squared is 1 over the permeability of free space times permittivity of free space. Question?
Is the definition of the meter based on the speed of light then?
Yes.
Okay.
So the meter is not a fixed constant. The meter depends on the speed of light. So if you were to do an experiment that said the meter is different, or excuse me, the speed of light is different, that would really be an experiment saying, the meter's off. Which is kind of why it really annoys me that they didn't decide to make the speed of light exactly 3 times 10 to the 8. Right? It's off by just a small fraction. And nobody would have noticed if you just changed the meter by some unmeasurable distance. But, they didn't want to have to go back and say, we're going to have to refigure all these calculations before because we changed the meter by 0.01% or whatever. Okay, let's move on. Here's the slide leading you into using calculus. I've already talked it through. So, once again, I have the equation written in terms of force. So now I have dF. Remember, d means infinitesimal. So the infinitesimal force due to an infinitesimal charge dq is given by, and otherwise it looks just like Coulomb's law. Now, I wrote this with 2 variations. Those are exactly the same thing. Remember, r hat has a magnitude of 1 and the direction of r vector. So by definition, r hat is equal to r vector over the magnitude of r. And so if you plug this definition in right there, it'll give you the other one. Sometimes it's easier using one form. Sometimes it's easier using the other. So I wrote it both ways just to make you think about, there are 2 different ways of writing. And it depends on my problem which one's going to be easiest. Now these were DFs. So if I want to do DE, all I'm going to do is get rid of the Q1s. So I'd have that, right? I just dropped out the Q1 because E is F over Q. So how do we solve problems with this? How are you going to do, for instance, the first problem on your homework? After today, I'm going to do essentially the first problem on the homework, so you'd better be able to do it since I'm going to do it in class. So how we use it is first, depending on the dimensionality of your charge distribution, right? Your problem's probably going to be a three-dimensional problem, but your charge distribution could be spread out over a line of charge, spread out over a sheet of charge, 2 dimensions, or spread out over a volume, 3 dimensions. So you have 3 different ways of doing it. Everything I'm doing today will be one-dimensional, just spread out over, actually no. I will consider higher dimensional. Most of what I'll do will be one-dimensional though. And so I will put dq is equal to lambda, the charge per unit length, times ds. Charge per unit length could be a constant or it could be a variable. So you have to be careful. What I'm going to do today will be constants. We're going to keep it simple. We have to break df into its components and solve each component separately. Now that adds 3 times the complexity, because instead of just having df is equal to k dq over r squared, I have df sub x equals df sub y equals and df sub z equals, and I have to do all 3 of those. That's part of vector calculus. So we're going to break df into its components and solve the components independently, and then in the end we can combine them. So let's run right into some problems. And some people might notice this first one isn't so difficult. So I'm going to have a circle with a charge at the center. Q2 is spread out along that circle. The circle has a circumference of L. And the question is, what is the force on Q1 due to Q2? How would you answer?
Isn't there no net force?
There's no net force. You want to think the problems through and save yourself the work if you can do it. I'm going to do this with half a circle so we can still do the work. But what's the reason there's no net force?
Because it's an even distribution. If it's right in the middle, then it's got even forces coming out of every direction.
Right. You have a symmetry argument. So you need to look at these things and say, do I have a symmetry argument that makes my life easy? There is nothing sloppy about using a correct symmetry argument to make your math much easier. So all I have to do with this is to observe what Jonathan observed, and that is for each little piece here of length ds, that's going to make a force. Let's assume Q1 and Q2 are both positive. What direction would the force be due to that piece right there on the center? If they're both positive, what direction would the force be? Pushing directly away, right? And so there's where my df would be, like that. But there would be a corresponding piece here that would make a force like this that would absolutely be the same magnitude, opposite direction. Those two would add up to 0. And then I just go around the circle, it adds up to 0 in every direction. And symmetry argument says it has to add up to 0. So we're going to take this and cut it in half. So now I'm going to say that Oh, there's a better way of doing this. There's a better way of doing this, but you know what? I don't have set up to do that. Cred. Let's see how much work it takes for me to do it the easier way. Or not the easier way, the better way. Add. Nope. Okay, forget it. We're not going to try to do it the better way. We're just going to do the original thing I wrote. So I'm just going to cut it off like this and say that all of this down here doesn't exist. Right, I was going to try to make a white box to cover it, but yeah, fail. So in that case, what would you be able to tell me about the net force? Using the same symmetry argument, it's going to have to point straight down. And even if I had used something that was less than half of the circle or more than half of the circle, you could just take the center of the hole and draw the line going through and say it's going to be all that direction, right? So we can make a symmetry argument always to make our lives easier. And so since we can always make the symmetry argument, I just drew it the easiest way to make my life easy. So now I'm going to calculate the force on Q1 due to this charge Q2 that's now spread out over, actually, let's keep it of length L just to be consistent and charge Q2 and just say, well, it's really only going to be half of length L and half of Q2 because we only have half of it. So you guys understand what I'm saying? So that means the charge density will be equal to Q2 divided by the length, right? Because that's what it would have been with the original. I was saying we're going to keep that charge density constant, cut off half of it. So there's my charge density, and I'm going to have dF magnitude, so I didn't write a vector sign, is equal to, since it's magnitude, I don't put the minus sign out front. I'm just putting K, I'm not putting K sub E because, well, we're in electricity now, so all our K is K sub E right now. dQ over R squared. There's my starting equation. But what is dQ for this situation? Go ahead.
If you're doing dF, don't you actually have another Q?
I do. You're right. I have the Q1. I wrote DE, which for your homework is what you're going to be doing. Okay, so thank you for the correction. What is DQ? Our starting, going through the process. I only had 3 steps, I think, on the preceding page. DQ, is this a linear distribution, an areal distribution, or a volumetric distribution? It's lineal, or linear, either word works, because it's spread out over a line. Now that line is bending, but it's still a line. It doesn't have a thickness, at least as far as we know. I know the picture looks a little thick, but it has no known thickness. So it's just a linear distribution. So it's a one-dimensional problem. It's a one-dimensional problem, but it's not a straight line. So that's going to be lambda ds. We have lambda up there, Q2 over L. I'm going to leave it as lambda right now because that's easier for me. Notice the radius here is going to be constant. The distance from Q1 to my wire is going to be constant. And so I can write that my dF magnitude is equal to K lambda Q1, get it in there, ds over R squared. Now I have to integrate over the length of the wire. So how would you integrate over the length of that wire? Well, actually, there's a step first before we do the integral. What was the step before the integral? I know there's only 3 steps, and I skipped the middle one. Do what? That is true, not what I'm looking for. To a capital, yes, because now I'm using the radius of the circle instead of R being the separation between the charges. Because the at every point the wire is a distance capital R from the center. So yes, there was an actual reason for it. What I'm looking for here is, this is actually a vector force, and I have to break it into components. So I have to, if I break it into components, I'm going to have to define my x and y directions. So I'm going to take, this is the origin where the center is, and define x and y. There's the x direction, there's the y direction. And so I'm going to say df in the x direction is equal to, so if we look at this vector here, let me define this angle as theta. My df vector is coming down here. This will be the same angle theta. So what would df in the x direction be if I have that angle theta? In terms of df magnitude. So I put df magnitude, and then how much of the df is in the x direction? Okay, it's x direction is the horizontal, which is adjacent to the angle. And so that means it's going to be cosine theta. And we do have to pay attention to the direction. I put x is positive to the right. What direction is df pointing? Yeah, so we got to have that negative sign. So now substituting what my df is, that's going to be minus k lambda q1 ds, that's cosine theta over r squared. How many variables do I have in that? Some are variables, some are constants. Is k a variable or constant? Constant. Is lambda variable or constant? Constant because it was made out of Q2 and L, which are both constant. Is Q1 constant or variable? Constant. Is S variable or constant? Variable. It's got to be variable, otherwise ds would always be 0. And is theta variable or constant? Variable. And I suppose capital R. Variable or constant? Constant. So we had two variables, s and theta. If I'm going to integrate, I need to get it down to 1. Which variable do you think it's going to be easier to get it down to? How many people say it's easier to get it down to s? How many people say it's easier to get down to theta? Okay. It was kind of 1 to 3. A lot of you aren't very clear on this. Well, it turns out it's much easier to get it down to theta. Because we know that ds, this little length out here, is related to the angle it goes through by the very simplistic ds is equal to the radius times d theta. Right? Arc length was equal to the radius times the angle. So d arc length is equal to radius times d the angle. And so that makes it real easy to write this as minus k lambda q1 r d theta cosine theta over r squared. I substituted for lambda here, so I put Q2 over L. The R on top canceled with one of the R's on bottom, so that's why it's only over R. So now my dfx is just an integral of a constant times cosine theta d theta. Pretty sure everyone here can do the integral of cosine theta d theta. So let's do that. And now we have to do what Nate was saying. We have to put in our limits, put in my constant out front. And what are my limits for that integral? 0 to pi, because the way I define theta, my arc starts at theta 0 and ends at pi. So going from 0 to pi, what's the integral of cosine theta d theta? Sine theta. So this is going to be minus kq1 q2 over RL times sine of theta final, which is pi, my sine of theta initial, which is 0. What's that? Does that make sense? Yes, because we already said by symmetry it had to be. Right? We did the part that was useless because I wanted to go through and make sure we know what we're doing here. So now let's do the y part. So now doing the y part, based on everything above, can you shortcut it for me?
Just exchange cosine for sine, right?
Yep, just exchange cosine for sine because the y component is also downward, so we're going to have the negative sign. And it's sine because we're looking at the vertical component there in my df. So I can shortcut everything just based on the work above. It's going to be minus k q1 q2 over RL sine theta d theta. So f sub y is going to be the integral. And let's put the constant out front again. Okay, so what's the integral of sine theta d theta? Negative cosine theta. Well, I had a negative sign out front, so negative and a negative is going to make it positive. Okay, what's cosine of pi minus cosine of 0? Negative 2. Because cosine of pi is minus 1, cosine of 0 is plus 1, minus 1 minus a plus 1, minus 2. So this is equal to minus 2 k q1 q2 over RL. So I've done Fx and Fy separately. So what is the net force acting on this? Force vector is equal to what? It's going to be 0 in the x direction plus this value in the y direction. So just minus 2k q1 q2 in the y direction. So there's my answer. Now keep in mind that answer is not for the original question, that's for half a circle. For the whole circle, it would have come to 0. Now it was a one-dimensional problem. How would you rate that on difficulty?
What's the scale?
Hard, medium, and easy. I don't want to get all technical. On a scale of 1 to 27, where 27 is requires a PhD. What do you think? Hard, medium, easy? Okay, medium to hard. Okay, let's go to another problem that's, again, a wire. But this would be a straight charged wire. Now I'm going to draw my picture to make sure we're clear on what's going on. So I have a straight wire. If you look at problem 1, it's a straight wire. What's different is problem 1 is a straight wire that we call a semi-infinite wire. And semi-infinite sounds wrong. Because what does infinite mean? Means what? Forever. How can you have something that's semi-forever? You know? Well, semi-infinite means it goes forever in one direction but not the other. And so the problem you have starts at the origin and goes off to infinity. Technically, it's of infinite length, but it has one ending point. So that's what makes it semi-infinite. So this is a finite wire instead of a semi-infinite. That's the only difference, really, in what we're doing. Well, that, and I'm flipping the problem over. And so I'm going to put a point charge here, Q1, and this point charge will be a distance P sub x from it horizontally, and a distance P sub y from the end of the wire vertically. The wire has a length of L with the charge Q2 spread out over it. And my origin is, again, I'm going to put it right at the charge. So we want to find the force. Actually, you know what? Let's switch this from force to electric field. What's the difference? I have to write one less Q in every single line. So let's change it to electric field. And so I'm going to say at P, whoops. And so instead of calling that Q1, I'm just going to put P is that point. Right, I said it's at the point. I divided by the Q1, hence I took out Q1 from my picture. It's the same problem. The only difference is in the end, I won't have the Q1 multiplied by it. And if I want to find the force, I just multiply by Q1. All right, so I've got the picture set up. Now let's start the nitty-gritty, very beginning. What's the first step in solving a problem like this? Determine if it's
Dimensional, two-dimensional, three-dimensional.
yeah, one-dimensional, two-dimensional, three-dimensional. Is that charge distributed over a line, over a surface, or over a volume? Over a line, so it's one-dimensional. So if it's one-dimensional, and if you look at your instructions, it tells you to identify the piece of charge. And so I put my little thing here. There's a little capsule. The charge dq is contained within that capsule. And that capsule, what's the height of this capsule? Okay, I'm going to put dy because it's in the y direction. You could have said ds. I think that's what you said, right? dl. Could have said dl as well. I just called it dy because it's in the y direction. Okay, so we've got that. And then we need to find what direction will the force or the electric field at point P be due to that charge. Assume that Q2 is a positive charge. So what direction is DE? And once again, you'll see on your problem, it tells you you have to identify this. And I'm actually going to use, no, I'm not. That would be too confusing. Perfect straight line. That's why I was going to use a tool to make a straight line. So there's the direction of my DE vector due to that little piece of charge dy that's in region dy. Now we have dq is necessary. If it's a one-dimensional charge distribution, what's dq equal to? It's equal to lambda dy. What is lambda equal to? Q2 over the length of the wire L. It sounded like you said R to me. Is that what you said as well? Nice. I like it when people are following along, know what they're doing. So I've set this up. What idea am I going to use to solve this? At this point, we only have one. But the question asks you specifically about your idea. So what idea am I going to use? The title of today's lecture. Coulomb's law, yeah. And that might have been what you said. You got to say things loud enough for me to hear, or I'm like, what? We're going to use Coulomb's law. So, it tells you to specify what you're going to use. You're going to use Coulomb's law here. And so if I'm using Coulomb's law, I am going to now find the magnitude of the force, break it into components, and integrate. So let's start with finding the magnitude of the electric field, So dE magnitude. So I drop the vector sign. What's the equation for dE? Okay, I drop off the minus because I'm only doing magnitude. So K, then what? Drop off the r hat because I'm doing magnitude. K times dq and over r squared. Now things are a little more complicated for that r. So how would I find r in this case? I have to use the Pythagorean theorem. R squared is equal to the x component, which is going to be px squared at all times, plus y squared, where y is how high it is. Notice y in my integral is going to start at py. It's not going to start at 0. So r squared is px squared plus y squared. I'm not going to substitute that in until I have to, because that's a lot more writing. And dq is lambda dy, and lambda is q2 over L, so we have that. Once again, I'm going to stick with the shortest writing possible. So I'm going to leave it like it is and go to my next step, break it into components. So if I break it into components, that means I need to have dE in the x direction and dE in the y direction. So have magnitude dE, how much will it be in the x direction? Once again, I'm going to define an angle, theta like this. So what's the x component of my dE? All but one thing. Yep. So there's my dEx. And what about dEy? Somebody said something, but I didn't hear it. Okay, it's the same except for you change it to sine. Because it's still down, so it still has the minus sign, but now sine for the opposite side. Okay, so that wasn't hard. Let's make it hard. That's what you wanted to do, wasn't it? Yeah, exactly. I wanted to make it hard, said no one ever. How many variables do I have there? Nope. Nope. I have 3. See, I knew we could make it hard. Let me show how that is 3. That's minus k lambda dy over r squared cosine theta. So r squared, that's a variable that depends on theta and y and theta. 3 variables. There are lots of ways to solve this, but there's only one that's easy, and that easy way takes a little creativity. Which variable do you think is going to be easiest to solve with? Okay, had a couple people that said y. If we do it with y, well, it turns out it's not the easiest. If we do it with y, then we're going to have r squared is px squared plus y squared. That's easy. We're going to have cosine theta is equal to px over r. So that's going to add in another r, but we've already done the r substitution. And then we already have the y. So what we're going to have, if we put it into y, is dex in terms of y is equal to minus k lambda dy over px squared plus y squared to the 3/2 power, and there's a px on top. Now, is that doable? Yeah, it's doable. I would solve that by getting out an integral table. But I have to use an integral table. If you do it in terms of y, you don't need the integral table. And in fact, if you do it in terms of y, it becomes trivially easy. Yes?
Do you mind explaining through the whole px and the over the 3/2?
Oh, okay. Yeah, I said that, but I didn't show it. So, that's erase. Okay, didn't mean to erase it. Wanted to keep that there. So if I make my substitutions, it's minus k lambda dy, no substitution yet, over for r squared, I'm going to have px squared plus y squared, right? So that's the first term. And then for cosine theta, I have px over r, so over the square root of px squared plus y squared, right? Cosine theta. And so I did the substitution for cosine theta there and the substitution for r, and then I combined them. I thought you wanted me to continue out with the integral, which meant I had to get out the integral table. I don't want to get out the integral table. I got to this in preparation. I was like, oh, no one's going to want to do that. You all realize that we can't just say u is equal to like px squared plus y squared, because if we do that, then we have a y dy, and we don't have the y dy, so it gets more complicated. So, not going to do that. Instead, going to do something that, like I said, it's a little tricky, but in the end, it's trivial. So where is it tricky? Well, let's start out by recognizing that I have my y variable and tangent theta are related. Tangent of theta is equal to y over px. Right? So that means if I take the derivative of both sides, what's the derivative of tangent theta? I like to write it as 1 over cosine squared, but yes. Now, since I did the derivative, I didn't do the derivative with respect to something. I just said derivative. I have d theta times secant squared. So I have d theta on top over cosine squared theta is equal to, and what's the derivative of y over px? Px being a constant. It's dy over px. And so now I can replace dy is equal to px d theta over cosine squared theta. So there's one substitution. I need two, right? Because I have to get rid of another variable. So I also need something to relate r with theta. So I come back and look at I already have it right here. Cosine theta is px over r. So that gives me a fairly simple relationship. R is equal to px over cosine theta. So I substitute those into my equation. And I've run out of both space and time, which sounds extra geeky. I don't know where I put that blank page. I thought I put it right here. Crud. That was beautiful. Well, substitute this R in. So coming back to this form in blue, so I'm going to write in green underneath the blue, equals minus k lambda. And for dy, I'm putting px d theta over cosine squared theta. So there's my dy. Divided by r squared, so divided by px over cosine theta quantity squared, and then times cosine theta. That's simple. What does it come out to be? What's 1 over cosine squared divided by 1 over cosine squared? 1. Hey, let's get rid of each other. What's px divided by px squared? 1 over px. So this is simply minus k lambda over px times cosine theta d theta. Now the cosine theta here was this one. So when I go to the dE in the y direction, it's just going to be minus k lambda over px sine theta d theta. So I have now pretty trivial integrals again, just integral over cosine theta d theta or sine theta d theta. The only thing I need now is to find the limits and I'd be good to go. Because we're out of time, I just come back here and I say, if I do the integral of sine, I'm going to have cosine. If I do the integral of cosine, I have sine. And so I just look at my geometry and say cosine of theta initial is equal to, I look at that and I say, well, px over square root of px squared plus py squared, right? That's my initial. And if I wanted cosine of theta final, instead of py, I would have py plus l in there. So py plus pl parenthesis quantity squared. So I find those values directly from my picture for putting it on the limits. Okay,